Okay, so as you see the board here, this is the framework that I want you to use to really build your knowledge foundation to make the segue from chapter 12 to chapter 13. And chapter 12, if you'll recall, covers mostly simple regression with some discussion on correlation analysis. And then chapter 13 covers multiple regression. So what I want to first do is talk briefly about the correlation analysis. And let me remind you that when I use the term correlation, implicitly I'm talking about the Pearson correlation coefficient. I will teach you later about the Spearman rank order correlation coefficient. But just as a reminder, correlation analysis is a test of association. Taking you back to, I think, video or mini lectures number maybe 17 and 21, if I remember correctly, I identified for you 3 different types of inferential statistics. 1 being test of differences, 2 being test of association, and 3 being predictive modeling. Well, correlation analysis is a test of association. Okay? Then in chapter 12, we moved from correlation analysis to simple regression. And let me just remind you that simple regression is a form of predictive modeling. Simple regression is really based on correlation analysis. It's just that in simple regression, we go from a test of association with correlation analysis to actually being able to do predictive modeling. And then in chapter 13, the conversation for Friday's class is multiple regression. And in multiple regression, that is also a form of predictive modeling. And not surprisingly, multiple regression builds on simple regression. Now what I want to do is briefly take you through each of the null and alternative hypotheses setups. So let's move back over to the correlation portion of the board now. And remember, this goofy looking P is actually the Greek letter rho. So when we do correlation analysis, our null and alternative hypotheses are set up as rho equals 0, rho does not equal 0. Now you could write the alternative for correlation analysis in a one-tail alternative. That's perfectly fine. So when we say that rho equals 0 in our null hypothesis, we're hypothesizing there that the 2 variables of interest are not correlated with one another. Or to put it another way, the 2 variables of interest, which both need to be scaled intervally or ratio, those 2 variables of interest are not linearly related to one another. So here we write our null and alternative hypotheses investigating whether 2 quantitatively scaled variables of interest are correlated with one another. Now when we go to the null and alternative hypothesis for simple regression, it's similar to correlation analysis, but it gets a bit more involved. Here we work with the null and alternative hypothesis having to do with the letter B. And if you think back to our earlier mini lectures where we set up the simple regression model of y equals a plus b times x, b is the slope of our line of best fit. B is also our approximation of the responsiveness of y to changes, responsiveness of changes to our dependent variable y to changes in our independent variable x. So our null and alternative hypothesis in simple regression is organized around this idea of, is the slope of b 0 or not? Now we could write the alternative in a one-tail sense. I just happen to have it set up in the two-tail sense here. And that's actually going to be far more common in any work that you do, okay? If the slope of the regression line is 0, then that means that x cannot be used to predict y, okay? So the other way that we could write the null and alternative with simple regression is with r squared rather than with b. Because remember, if the slope of b is 0, by definition, the regression model does not help us predict our dependent variable. Thus, if the slope of b is 0 and the regression model does not help us predict our dependent variable, that means the variance explained is 0. So our null alternative is 0. Notice here the alternative hypothesis, r squared, is greater than 0. There's nothing special about that other than the fact that whenever you square r, whether r is negative or positive, whenever you square r, you're going to get a positive number, okay? So there's no way mathematically that r squared could be less than 0. And that's why we write it as such, okay? But again, in simple regression, one independent variable used to predict the dependent variable. Here's how we set up our hypotheses. Now, multiple regression is one, in some ways, small extension of simple regression, but it certainly adds a level of information and complexity. Let me first take you through the null and alternative hypotheses on the board. And notice here, I want to take you back to the simple regression screen for just a second. Notice here, I set up this set of null and alternative hypotheses, and I use the word or, and then this set of hypotheses. If b equals 0, by definition, r squared equals 0. So whether we test our null and alternative hypothesis with b or with r squared doesn't make any difference, because if this is true, by definition, this is true. In multiple regression, we've actually got two levels of hypothesis testing to do, okay? The first thing that we do is we ask the question, does the regression model help predict the dependent variable? And the way that we answer that question is, if you look in the multiple regression output, you'll see the quote-unquote ANOVA table, and the p-value in the ANOVA table of multiple regression, that's where we ascertain whether r squared equals 0 or whether r squared is greater than 0. Or in other words, does the regression model in the aggregate help predict the dependent variable, or doesn't it? Okay? But in addition to asking the question about the whole regression model, we must also test hypotheses for the predicted slope of each of our independent variables. And that's why I have here my null and alternative hypothesis for the entire regression model. But then instead of saying or, as we did with simple regression, we say and, because we have to do both this and this. This addresses the whole regression model. This side of the hypothesis testing addresses each of the predicted slopes for each of our independent variables. So here I have the null hypothesis is b1 equals 0. The alternative hypothesis is b1 is not equal to 0. And we continue that out, as you see here on the far right, the null hypothesis b sub n equals 0, b sub n does not equal 0. And I set that up so that, let's say we had two independent variables, so it would be b1 equals 0, b1 does not equal 0. We would also have a null and alternative that says b sub 2 equals 0, b sub 2 does not equal 0. Just because we conclude that the regression model helps predict the dependent variable doesn't mean that every independent variable in our model is going to help in that prediction. So again, we first test the whole model, then we have to test whether each of the individual predictors significantly helps. Now, again, I want to go back over to the simple regression model momentarily. And let me remind you that this is the basic model for simple regression. And notice here, I just say y equals a plus b times x. I don't use any notation here because there's only one independent variable. Now, when we segue to the multiple regression model, look what happens here is we have one independent variable, we have two independent variables, and it can go on out until we have what we call n independent variables, okay? So for each independent variable, multiple regression output generates an estimate of how much impact on the dependent variable, does our x1 predictor variable have. We get a separate indicator of how much impact on our dependent variable we think our second independent variable has. So again, I want to go back up to this part. This asks the question, does the whole regression model help predict the dependent variable? This portion of the hypothesis testing asks the question, does x1 help? Yes or no. Does x2 help? Yes or no. If we had a third independent variable, does x3 help? Until finally we get out to n number of independent variables. I remind you here that this is another methodology of predictive modeling in terms of the three groupings of inferential statistical tests: tests of differences, tests of association, and predictive modeling. There's one final thing I just want to mention here before we actually move to look at some computer output. And in multiple regression output, you'll almost always see the values for R squared and then what they call adjusted R squared. I'll handle through a memo more detail on adjusted R squared, but let me just tell you as a matter of practice, when you're reading multiple regression output, you need to pay attention to the adjusted R squared and not to the R squared. Okay, so just as a word of guidance, if you want to say, well, how much of the variance in my dependent variable y is explained by my regression model, you should look at the adjusted R squared number rather than the R squared. Okay, so that's a general overview of how we make the segue from correlation analysis to simple regression analysis to multiple regression analysis. Hopefully now it begins to sink into you why I place such great importance on you've really got to understand correlation analysis, because that's what gives us the springboard to simple regression. And once you understand simple regression analysis, I'm telling you, to follow multiple regression is not that big of a deal either. So I hope this helps. And the next thing that we'll do is take a look at some computer output for multiple regression. Thanks.